So let's go and have a game on this seesaw. To see where the centre of mass is. So here we have our non-uniform seesaw. It has a mass of 120 kilos. So because Amy and John are sitting at opposite ends, I'm going to call the seesaw AJ, label the ends AJ. Now we're trying to find the distance from Amy and Charlotte to the centre of mass. So I'm going to call that distance x. So there's the distance x to the centre of mass, and the force at the centre of mass is 120 g. Okay, so we've got Amy and John's masses are 62 and 85 kilos respectively. So that will lead to forces at those ends of 62g and 85g. And the seesaw has got a length of 3 meters supported at its center. So there's the pivot point. A normal reaction at the pivot point, which is right in the middle of the beam or seesaw, 1.5 meters from either end. So then we've got Jack and Charlotte sitting with John and Amy. So Jack sits with John, Charlotte sits with Amy, and their masses are 28g and 35g. The masses are 28 kilos and 35 kilos, so the forces are 28g and 35g. So when I've got a situation like this, we know that the beam is in equilibrium. We can resolve forces in any direction, and in this case the vertical direction makes the most sense, the only sense really, and we can also take moments about any point, and the resultant moment will be equal to 0. So if we look at the resolving forces first, we've got R going in the positive direction. If we resolve forces, taking that as the positive direction, and then we've got 62g, 28g, 120g, 85g, and 35g, all in the opposite direction. So therefore R must be equal to 330g. So the next thing we're going to do is take moments about a point. Now, what point makes sense? Well, actually, we could, if we decided to take moments about R, about the midpoint, then we wouldn't have needed to find R. We wouldn't have needed to resolve, but it would have been a little bit messier because x is the distance from A. So what I'm going to do is I'm going to take moments about A, since I've already worked out what R is. So taking moments about A, these two forces have got no moments about A because they are both acting through A. The moment of this force about A is a clockwise moment, so I'm going to take that as positive. So that's 120g multiplied by the distance. And then I've got R in the opposite direction, it's in the anti-clockwise direction. So that's why this is a minus here. And then it's R times 1.5. And then these two forces are both in the clockwise direction, the same direction as the 120g. So we've got plus 85g times its distance, which is 3, plus 35g times its distance from A, which is 3. And when we work that out, we know what R is. We can substitute R in, that's 330g. And we've only got one there unknown, which is x. We can solve the equation for x, and we get x is 1.125 meters. Does that look sensible? Yes, it does. It's to the left-hand side of the pivot point. We've got more mass on this side than on this side. So to balance things up, the mass of the beam, the seesaw, needs to be to the left of the pivot points. Okay, so what is the distance from Amy and John to the mass of the to the centre of mass of the seesaw? We've answered that question. We've got to state any modelling assumptions. Well, we've modelled the seesaw as a non-uniform rod so that it doesn't bend and it has no thickness or no width. So we don't have any complications with distances or this sort of thing. And the people are all modelled as point masses with no dimensions, so that we can place them exactly on the ends of the rod or the seesaw. So there we are.